So when deciding which method to use for each of these, there's a couple different ways that people approach these. Some people will start by looking at the equations and look at, like, for this equation, which method would I use? And that will work, but I tend to find that takes a little bit longer than some other alternatives. I tend to find it's easier by taking a look over here at the three methods that I need to use, and then looking to see which one would I apply each of these to. And really, they're written in the order that I tend to do it in. The very first thing I try to look for is I try to look for the one that uses square root principle, or square root property. Basically, that's just the one where we take square root of both sides of the equation. Okay, so that's all that's talking about. So if I'm going to be using square root principle on, let's say I try to use it on that first one, I'd have to get the squared part by itself first. So in that kind of a case, that would mean moving the 8x and the 15 to the other side, and then we'd take the square root of both sides at that point. But is this really doable? Can we simplify that square root?
No.
No, because we got that x in there along with the number. Now, if it was just the number inside of the square root, we could deal with that. And that would actually help us. But because we have that x in there, that's not the way we're going to want to do it. So we cannot use square root principle. And so notice what told us that. It's because we had both the x squared and the x. So knowing that, which one of these equations, the first, the second, or the third, should we use for the square root principle? Yeah, it's going to be that third one. Because you notice the x only appears once. And so that's kind of what you look for. Is if you have an equation where the x only appears one time, then we can solve it by doing square root principle. So like I'd add the 64 to both sides, and then I'd go ahead and I'd take the square root of both sides at that point. But now, when I do that, when I do the square root of both sides, take the square root of 64 there, what do I need to remember to include when I take the square root of both sides? Yeah, that plus or minus. So it would actually have to be plus or minus root 64. If anything, that's the part that we get a little bit rusty on there. And so include the plus or minus whenever you create the square root in the process of solving it through. All right, next up. You would then look for factoring. I'll tell you, only one of these can be solved by factoring. So figure out which one's factorable, and then that will tell you which one's quadratic formula. The great part about looking for factoring on these is that each of these two equations, you notice, just start with the plain old x squared. So we don't have to worry about using a particularly fancy method. We don't have to do a times c to use the grouping method or anything like that. All we have to do is figure out what two numbers add to the middle number and multiply to the last number. So I look to see, is there such a combination for this? Are there two numbers that add to 8 and multiply to 15? Yeah, 5 and 3. So yes, there is such a combination, which means then that I would solve that one by factoring. Now, if I were actually having to go through and do the solution, that means I'd write it out as x plus 3 times x plus 5 equals 0. And then we could finish solving it out from there. Remember, I'm setting each of the parentheses equal to 0. So like in that case, if we actually did have to solve it out, we get x equals -3 and -5. Of course, I didn't ask you to solve them out. You didn't have to do that. I'm just kind of bringing this up, jogging your memory. Now, this middle one here that we haven't dealt with yet, is that one factorable?
No.
No. There's no two numbers that add to 2 and multiply to 30, which is why we have to use quadratic formula with it. And so, now, that's the one that we would have to use quadratic formula with, but could I have used quadratic formula with the first one? Yes, I can use quadratic formula there to solve it. Now, in this particular context where we had to use each method once, no, but in general, yes, we could still use quadratic formula there. You technically even could use quadratic formula there, but first of all, why? And second of all, because there's no b value, so b0, that can sometimes lead to problems in questions. So it's better off to actually stick with quadratic formula only when we need it. Especially because quadratic formula, of course, is big and complicated, and it's prone to error, right? Because there's so many moving parts in it, we have to be really careful not to make mistakes. That's why I always like to look for factoring first, because if you can factor it, you're much less likely to run into errors along the way. And on this set here, I again do want to start the same way I started the last one, which is figuring out which one do I want to use square root principle for. So which of them will we use square root principle here? The first, the second, or the third? Yeah, it's going to be the second one there. Because you'll notice that in the second equation, the x only appears one time. And so like if I were going through and solving this, I'd have to start by getting the squared by itself. So we do x minus 4 squared equals, in this case, negative 13. And then I could get rid of the squared by taking the square root of both sides. And remember, when we take the square root of both sides, that just cancels out the squared on that left side. On the right side, what would I need to remember to include? Yep, plus or minus. So it'd have to be plus or minus that square root. Now, we actually aren't going to solve that one through, partly because this one actually runs into some other issues along the way, but that would be the right method. So now, having done that for square root principle, there's just two equations and two methods left. When figuring out these, figure out first which one of them is factorable. Right now, both of these, when we do look to factor them, notice both of them are 2x squared, and just instead of just x squared, like we saw in the last problem. And so, for doing the factoring on these, either you're just really good and have like that instinct down, you can just look at them and come up with those factorizations pretty quick, or you might be using the grouping method, where the very first thing we do is we figure out what a times c equals. And then the next step would be to figure out, are there two numbers that add to the middle number and multiply to ac? So looking at that first one up here, are there two numbers that add to 6 but multiply to 10? Nobody's coming up with anything. So theoretically then that last one should be factorable. So let's check that. Are there two numbers that add to 11 and multiply to 24? Yes, for that last one, 3 and 8 would add to 11 but multiply to 24. And so that's what we would use. Now, again, a little crash course reminder on how we do that factoring there, because it's been a little while since we've done this dedicated kind of factoring work, because I have seen that since it has been a while that I've seen a few people who then say, oh, it's 8 and 3, so it's going to be x plus 8 times x plus 3. But it's not. Because, of course, in this case, when I did the x times x, that would just give me x squared, not the 2x squared that I need. So what do we do with the 8 and the 3? Just kind of reminding you, we're using the grouping method here. And so I would be breaking up the 11x into 8x and 3x. Now everything else is still the same. So I still have the 2x squared, and I still have the plus 12, and it's still equal to 0. And then we factor out of the first two terms, and we factor out of the last two terms. And so hopefully this is already familiar, you remember this well already, but just in case you were getting a little rusty on it, it's kind of bringing it back, making us remember so that we remember what that factoring is going to look like. Because of course if we can do it with this factoring method, that's going to be a lot more reliable than having to go and use the quadratic formula instead. And so like if you were doing it by factoring, that would then be your final answer. But since it is factorable, we know that's factoring method. And so process of elimination tells us that the top equation must have been quadratic formula. And yes, it is, because I cannot use square root principle and I cannot use factoring. Therefore, we would have to then resort to quadratic formula. Now, could you have also used quadratic formula on this bottom one? Yes, you could have. And if you're having trouble with the factoring, that's kind of your fallback position. You can still go and use that. Could we have used quadratic formula on this middle one? Well, technically yes, but if you do try to use it on something like that, you'd have to start by multiplying out this x minus 4 squared, which is not x squared plus or minus 16. Because remember, you'd actually have to do like x minus 4 times x minus 4 and multiply everything in the first by everything in the second. And then you'd have to add the 13 to combine like terms, and then you could plug it in. That seems a lot harder than using square root principle to me. So I would definitely recommend that whenever you see just that x appearing once, stick with just doing it algebraically, just using the square roots of both sides.